So welcome everyone, welcome back to the session with Classic. And today we have Eden once again for the third time to talk about quantum primitives with Classic. This will be the third session in the series. So if you have missed out any of the previous lectures, I would just scroll through the playlist on YouTube, go to the previous two lectures by Classic, and then return back to this video. And yes, Eden, the stage is all yours. Over to you.
Perfect, thank you. So can you hear me well and can you see my slides?
Yes.
Perfect. Okay, so hello again, everyone. So now today we are going to dive into the second part of part 2 of quantum primitives with Classic. So by the end of today's session, you will gain three main things. So one, you will understand how to qualitatively assess the dependency of an expectation value on number of shots. So this we will go back to the previous session, and then we'll go a bit over the homework exercise that you had, and we have some insightful things to discuss over there. Then we will understand the next two quantum primitives we want to discuss. So one is the phase kickback, and the second is linear combination of unitaries, including hands-on implementations, as we always do in this part of in this model that we have. And some of these two quantum primitives are a bit more advanced. So some of them you will implement during the homework. We will touch on small implementation or small scale implementations of these primitives, but by the end of today's session you should understand what are these and how to implement them hands-on. And three is understand when to use these quantum primitives, and this will be especially useful when we come up to the project phase and we want to use all the knowledge that we acquire throughout the model and to actually implement those things and to implement state-of-the-art papers that demonstrate some quantum advantage. So let's start with the dependency of the number of shots. So let's do a quick recap from the homework 2 that you had and from the previous session. So we discussed the swap test and the Hadamard test. Now this is the Hadamard test, and this is the example from the homework that you had. So I wanted you to evaluate the expectation value, or the real part of the expectation value, of the quantum Fourier transform unitary in the state 0 with 4 qubits. So this was the task, and I wanted you to execute it with 1,000, 2,000, and so on, and at 16,000 shots, and to explain the results. So this was the homework assignment. I hope it was useful. I've seen some very nice submissions already. And one of them was by Saba Bozpolat. I hope I pronounced the name well. And this is the plot that she had. So what we can see on the x-axis is the number of shots. And on the y-axis, we can see the expectation value. So already is the theoretical expectation value, and this is the correct expectation value that the theoretical expectation value. So it's 0.25. This is what we expect theoretically when we calculate with pen and paper. Now on the blue, we can see from her plot that as we progress towards the number of shots, there is some difference. As we increase the number of shots, it might seem that we getting closer and closer to the theoretical value that we aim for, but it's not that clear from here. And as part of the submission, she wrote, it is important to draw attention to the randomized nature of quantum physics here. Due to this inherent behavior of quantum computation, each performance of this notebook will yield a slightly different outcome. And this is exactly right. So what I gave you as homework exercise was maybe a small part of how you should understand the bigger picture, and now we will going to discuss the bigger picture. But I wanted you to explore it by yourself and to come to the right conclusion by playing around with the actual implementation. So this is very useful tool when we design quantum algorithm and we actually trying to implement them. So to play around with the implementation, tweak the parameters, tweak the number of shots, play around with the hyperparameters that we have of the algorithm in order to get a better feeling and better understand what's going on. So what we have here is on the x-axis, the number of shots. On the y-axis is the expectation value. Again, on red is the theoretical value. And in blue, these are several experiments or several execution of the same algorithm, of the same quantum circuit implementation with 1,000 shots. So I implemented the algorithm, I ran it with 1,000 shots, and then I received this value. So 0.29 something. And then I did it again and I received this value, and so on and so forth. So here we can see 5 different implementation of the same, 5 different executions of the same algorithm with the same number of shots, so with 1,000 shots. And this is the span that we received. I did it again with 2,000 shots. So these are five different executions. So I ran it with 2,000 shots one time, and then I did it again and again 5 times. And these are the expectation values that I received. And I repeated that for 4,000 shots, and for 8,000 shots, and for 16,000 shots, and for 32,000 K shots. And we can see here, so now we can see the dependency, or we can have a qualitative understanding on the dependency of the number of shots. So what can we see? We see that as we increase the number of shots, the standard deviation, or how we deviate from the theoretical value, getting smaller and smaller. So we converge to the theoretical value, but it's not enough to understand it from one experiment that we do. We need to do some multiple experiments of the same number of shots in order to see it actually that we converge into the theoretical value, right? And I think this graph demonstrates that fact quite clearly. So if I can summarize what I just said on a more mathematical note, so the expectation value is a classical random variable, right? So it has a mean and it has a standard deviation. Now, the mean is constant for all constant in terms of the number of shots, right? So we can see that all the span of all the experiments here with different number of shots is around the theoretical value, right? But what is different is the standard deviation, how the difference between the different experiments, so how we deviate from the mean value or from the theoretical expectation value. And this is something that is interesting in terms of coming to implementation of real quantum algorithms. So what is this dependency? So this increases the standard deviation, decreases as 1 over the number of shots, or 1 over square root, or 1 over nth number of shots squared. So these numbers are interesting, or this how we decrease, it's interesting when we come to real implementations. So this is the high level thing that I wanted to discuss in terms of the homework assignment. Plotting this graph wasn't part of the homework, and you still have time to submit the homework, but I wanted to give you a broader understanding on the dependency of number of shots and how you can get a feeling. So sometimes from one experiment that we do, it's not enough to understand the dependency or to get a better feeling. So sometimes we need to repeat it. And then also we can think about the expectations value as a classical random variable. And I think this notion on this way of thinking is sometimes quite useful, because then we can assess it in a better way. And then we can also sort of in our mind decompose or separate the quantum nature of the quantum algorithms and the classical probabilities of the algorithm or the measurement. So there's some mix between the quantum randomness and the classical randomness, and this looking on this expectation value in this way can make the separation a bit clearer. Now, in terms of relation to the project, I wanted to print screen the one of the papers. So this is evidence for the utility of quantum computing before fault tolerance. So this is one of the 3 papers, the 3 key papers that you will implement as part of the phase 1 of the project. And in the abstract, they say they explain what they did, and they say that they evaluated or they measured accurate expectation values. So now with the Hadamard test, you will have one tool in your tool set, a toolkit, that you will be able to actually evaluate this expectation value in an accurate way. And you will know, and you have the ability to do it hands-on with a building block or with a quantum primitive that you already implemented throughout the model. So this is one of the key quantum primitives that you acquire, and then you will be able to actually use them in the implementation of these one of 3 key papers. Okay, let's continue, and let's start with the first quantum primitives of today's session. And this is a phase kickback. So we'll cover the general scheme of the quantum algorithm, the definition, and we'll give intuition. And then we'll go through the implementation, and then you'll have the hands-on exercise that you'll do yourself. So the general scheme of quantum algorithms in general, not just the phase kickback, but the way we can view general quantum algorithm. So the first step is to encode the data into the quantum algorithm. So it's not only for a quantum machine learning task. When we think about it, so the structure of the algorithm is also sort of encoding the data. So at the end, we want to have a quantum algorithm that implement something interesting in the classical world as well, even if it's a Hamiltonian simulation or simulating a molecule. So we want to encode the molecule or some parameters of the molecule, or we want to encode something into the quantum algorithm. So this will always be the first step in the algorithm that we make. Then the second step is to evolve the algorithm and exploit interference patterns in the Hilbert space. So this is the step that we actually gain some advantage by evolving or by doing the quantum computation or the quantum algorithm development. And the last phase is to measure the algorithm smartly and then post-process the measurement. So roughly speaking, we can view quantum algorithms in the eyes of these three steps. And today's the quantum primitive that we're going to discuss now, the phase kickback, is sort of between the encoding part and the evolving part. So we can view it as a mixture of both. And now we'll get into the real definition. So the input, when we speak about the algorithm, is a function, a classical function, f, that goes from an n bit strings to a bit, a classical bit. And we have a quantum state x, and of course, it can be in a superposition of other states as well. The output is a quantum state where the phase of x, or for each value, is -1 to the power of f of x. And in short time, we will go through an example, but I think most of you already know it, maybe not knowing that you actually know it. But for example, in the global algorithm, the phase kickback is used there extensively. So probably you've seen something like this, but maybe you didn't understand that you can think about the part of the algorithm that you know as a quantum primitive that is useful also for other algorithms and tasks. And when it is applied in a superposition of states, so let's say we think about the state as a superposition of integers, so from 0 to 2 to the power n-1, and then for each one of the components of the state vector that we have, we apply the phase kickback, or the phase kickback is applied in the superposition. And it's called phase kickback because in a moment we'll see how we kick back the value of the function f of x from being in a different state to the phase itself. So we kick it up basically to the phase, and this is why it's called a phase kickback. Now let's go through an intuition and some example. So we will understand it through the concrete example of the function f of x goes from a 2-bit string. So it can be the input to the function. The classical function can be 0, 0, 0, 1, 1, 0, or 1, 1. And we interpret this as an integer. So 0, 0 is the value 0, the decimal, the integer 0. 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. So f of x equals x equals fs, equals 0. So what does it mean? Only when we receive the bit string 0, 0, the value of the function is 1. Otherwise, it's 0. Okay? And the second input that we'll have is a superposition of an equal superposition of all the values between 0 and 3. We can depict this kind of state in a graphical way as a vector, right? So we are dealing with linear algebra, and we have a pictorial way to demonstrate our linear algebra. And this is especially useful for this kind of quantum primitive. And I think most of you will know it from also the Grover algorithm. So we can depict it this way. And now we want to decompose it into two-state vector. So we have the state vector of 0. So it has, if we project the state psi on 0, so there is some component of psi on the basis of 0. And then the second one, which is orthogonal to the state 0, is is the superposition of 1, 2, and 3. Now, what's the phase kickback does for this kind of graphical pictorial way is we flip the phase of the component of 0, right? So as we've seen earlier, we have -1 to the power of f of x. So we have -1 to the power x equals 0. And only when x equals 0, we receive a minus phase. So in a graphical way, we can understand it as we flip the vector across the component of the 0 state. So we take the state vector from here to here. And now if you remember the graphical way of understanding Grover algorithm, so we have in Grover another reflection operator, and then we converge to the desired state. But this is the same as we have in Grover. So this is the small component in Grover. So this is the way we can represent this reflection, right? So the reflections come from the phase kickback. And this is the way we can understand it in a graphical way. So giving the phase, having the phase of minus of a specific value that we want, a desired value, and flips it across the component of one of the components of the state vector. Now, in order to understand it, we need to understand also the meaning of an oracle in quantum computing, in quantum algorithm. So the oracle of F takes an input and a quantum state with n bits and a qubit or 1 qubit, and then it doesn't change at all the state of x. And for the state of y, for the state of qubit, it applies y XOR f of x, right? So f of x can receive the output of the function is only 0 or 1, and y can be 0 or 1 or in superposition. But this operation, the XOR, means that if it's exclusive OR. So if the value of y is 1 and the value of f of x is 1, so the output of the XOR, so this evaluation operation is 0. So XOR means if we have only 1, 0 and 1, 1. So let's do another example. So if the value of y is 0 and then f of x is 1, so 0 XOR 1 will be 1. And this is a definition of an oracle, and this is the way we encode or evaluate function on quantum algorithms with the oracle model. Now, what we want to do in phase kickback is to exploit this oracle model or to use it in some transformation. So always we use as the input qubit the state minus. So, and there is a mistake here, so it should be -1, not +1. But we always use the state minus for this. And the fact that we use minus, and this mathematically we'll cover later and we'll go through the tutorial, but it doesn't change the state minus at all. What it does, it applies the -1 to the power of f of x. So the way we use it is quite simple. The mathematics is a bit more evolved, but it's also quite straightforward and you can implement it. So what you should have in mind is that we have the oracle model, and we use this oracle model to implement a phase kickback. The way we do it is with the input qubit in the minus state. So this is the high-level explanation of how we implement and how we do this phase kickback. Now, let's go through the example, the implementation, how we do it for the oracle of the example we discussed graphically before. And then we'll go through the implementation itself. So in today's lecture, we won't cover the mathematics. So this will take a bit more time, and I recommend you to do it offline. And you have the tutorial, in the tutorial that I will show you soon, you will have the actual mathematical implementation throughout. So the mathematical description of how we come to this throughout the tutorial. But now we want to go over the high-level explanation, intuition, and the implementation of this specific example. So we covered it in a graphical way. Now we'll cover it in implementation-wise. So what we want to do is to have, we have the oracle, right? So let's start from the beginning. We have the oracle. We want to apply a phase kickback using this oracle. So we have the oracle. For this specific example, we want to evaluate for the function when x equals 0. Now we have an input, a target we call it, and the output of this oracle is target XOR the function that we have. So this is the function f of x. It's either 0 or 1, and this is the output of what we get. Now, what we have here, we can implement quite intuitively with Qmod, with the native language of Classic. So we create this oracle function. It has two values. So it has target, this is target, and it has a quantum number. So as we said, the quantum number is a quantum register. So here it's with n qubits, but it has some mathematical interpretation. So here we interpret it as integers. And what we have within the function, so this is how it implements all the diagram, the scheme that we see here, is we're doing target equals or XOR equals x equals 0. So this is exactly what we want to achieve here. And this is how we actually implement it on a quantum algorithm, right? So on the bottom, we see the scheme. And on the top, we see how we can implement the scheme quite intuitively with 2 lines of code or with 3 lines of code using the native Qmod language. Now, the second step is that we want to have as an input the minus state, right? And what we said earlier is the output on the same, so the minus state, if we input the minus state as the qubit, it doesn't change at all. And what we receive is -1 to the power f of x. So this is what we want to implement now. Now, in order to achieve this minus state, we have some algorithm or some function that applies it, and we initialize, as always, with the 0 state. So this is the code that actually implements this prepare minus. So we prepare the minus state. How we do it? We initialize 1 qubit. So allocate is initializing the qubit in the state 0. And then we apply the X gate. After it, we apply the Hadamard gate. And this is how we go from the 0 state to the minus state. So this is the second step of our quantum phase kickback algorithm. So first we prepare the oracle, and here with Qmod, you don't need to understand how the underlying implementation works, because there can be also sometimes many possible implementations of this oracle. But what we're interested in is in the functionality, right? So here in the oracle, we describe the functionality, the function itself. So the function is x equals 0. And in the exercise in a few minutes, you will need to actually implement a different function. But you won't think about the implementation, how to implement the quantum circuit, because this is we want to focus on the high-level functional design and to give some automated to the classic synthesis engine, the compiler, to actually come up with the implementation itself. So here we're focused on the high-level algorithmic capabilities that we want. So we have the oracle function, we have the prepare minus function as well. So these are the 2 functions. Now, specifically for the case with the minus state, and this is the case for the phase kickback, at the end, we want to bring back the qubit to the state of 0. And then it will be completely disentangled from the quantum number x. So the way we do it is with the construct within apply of classic. So now we define the function oracle phase kickback. And what we do, we have the target. So this is the qubit we have in bottom. And then within, so we first prepare the prepare minus. So this is the within. And then we apply the oracle function. What the within apply does, it applies the function that we want. And then it applies the oracle function. And then it applies the inverse function of the prepare minus. Because sometimes, or it's a common method in quantum algorithms that we want to have in unitaries, it's U, V, U dagger. So for example, here the U, the unitary that we want to make is the minus, and then V is actually the operation itself we want to prepare. And then we do U dagger because we want to inverse the first operation. So we can think about it as a change of basis or applying the function at heart, the apply, in a different basis. So we do a change of basis with using the U, and then we apply the operation V, or here it's within the apply, the function that is as written below the apply. And then we want to go back to the original basis. So we do the inverse of the first operation, the operation that is under the within scope. So this is the oracle phase kickback, right? So we have the quantum number x. This is the input. And what the oracle phase kickback does is it changes it adds a phase of -1 to all the values that the function is evaluated for this given x. Now we want to tie it and to have a complete algorithm. So this is only the function itself, but we want to apply it on to initialize this number x and then to apply it on something, right? So we want to apply it as the example before, on a superposition of the state 0, +1, +2, +3. So in an equal superposition. And what we will expect to receive is only a minus phase of the 0 state. And then all the other states will be, the components of the state will be with no phase change. And this is the phase kickback. And we want to start with, again, with the 0 state of 4 qubits, or 2 qubits. This is what we have always. So how we do it, we have the main function. This is the general function that we use. And then we allocate, we initialize x with 2 qubits, and then we apply Hadamard transform. So Hadamard transform transform the value, the quantum number x, to an equal superposition of all possible values with this specific number of qubits. And then we apply the Oracle phase kickback. So what we can see here is we decomposed this phase kickback primitive, this phase kickback algorithm, into functional building blocks, and then we build them one by one. So now we can view it from the last hierarchy. So we have the main, and let's do it down back. So we initialize the quantum number x with 2 qubits. We apply a Hadamard transform, so we put it in an equal superposition of all the states. Then we have the Oracle phase kickback on x. So we want to flip the phase of the component 0 when of the value of x after we applied it in a superposition. So what is the Oracle phase kickback? It initializes additional auxiliary qubits, the target qubit. So this is the qubit on the bottom in the scheme. We prepare this additional qubit in the minus state. This is what we want for the Oracle phase kickback. And after we apply it in the minus state, then we will inverse it at the end. But what we want to do is to apply the Oracle function. And the Oracle function receives this x and the auxiliary qubits target, and it applies the target XOR equals when x equals 0. So this is how we can think when we design the quantum algorithm in a functional level. So we build the different functions, and then we use it and we compose it. And we are not interested now in the implementation itself because we designed the algorithm. The next phase, of course, will be to actually synthesize and come up with the underlying implementation. And this is done automatically with this compiler, the synthesis engine. And then we can play around with the different implementations. And we'll see that even for this example, there are several implementations that can be done using more auxiliary qubits or less auxiliary qubits, and the trade-offs between the circuit depth and the circuit width, and all the available constraints and preferences we have. So in the classic platform, you have under tutorials, you have the phase kickback algorithm, the phase kickback example, and this is exactly what we covered here. So you will open it in a few minutes and also at home, and then you can open the example itself. You can view the code. So again, this is the code written in the native Qmod, and we can see according to the Qfunct. So the quantum functions, we prepare each quantum function, and then we use them within the code. And we can press synthesize and actually view the underlying circuit implementation. Now, before we go to the platform and then we cover the exercise that I want you to do now, I want you to give you some examples where this phase kickback is used. And so first, this is the original famous algorithm by Grover. So here we can see the author is Love Grover, a fast quantum mechanical algorithm for database search. And this is from the paper, and we can see the exactly, or not exactly, but a very similar schematic way to present how this phase kickback goes. So this is applied on a specific, with a specific function. I think it's inverse across the average, but we can see the phase flip. So we flip it from a plus sign to minus sign or vice versa. And this is done using this phase kickback primitive. Now, another example, which is more recent and is useful for many application, is quantum walk speedup of backtracking algorithms. So this is a family of algorithms, and then from this quantum, the framework of quantum algorithms, we can see this is on the more mathematical way. So here it's a graphical way of explaining the algorithm and understanding it. So when you view papers, you can view it sometimes in the graphical way or in the mathematical way, right? So here we can see a -1 to the power of some classical expression as the coefficient of the components of x. And when you view this way, you know that a phase kickback is somewhere in the picture, and if you need to implement it, you will need to use some form of phase kickback. So these two hints, you can call them, are will help you throughout the project and throughout your career when you see some mathematical structure of -1 to the power of classical expression as a coefficient, or when you view that you should flip the state vector in a graphical way across some component or across some other vector, you should feel the familiarity with the phase kickback, and then you have the understanding that you will come to the phase kickback when you need to implement this kind of primitive with algorithm for a general frame. Move to the platform. So now I'm in the classic platform, and so here from the classic platform, if I go to the model tab, and then we go from tutorials, we open the phase kickback tutorial. And this is the tutorial, the example we covered here. Beside one small change that we have this with 4 qubits. Now I can change it to initialize with 2 qubits, and then I can synthesize. These are some errors, I think, from previous experiments. So here we can see the actual algorithm, right? So here we have the Hadamard transform that we apply on these 2 qubits, and the Hadamard transform is just 2 Hadamards. And then we have the prepare minus. So we do a NOT and then a Hadamard gate on the target qubit. So this is the auxiliary qubits that we have. At the end, we do Hadamard and NOT to inverse the first operation. And then we have the oracle function. So the oracle function is, as in the example we covered earlier, is x equals 0. So here we have within the implementation. So now we are already seeing the functionality of the compiler itself. So we didn't define arithmetic. We defined the oracle function to be some arithmetic value. Now we can zoom in, and what we sense here and what we view as the next functional building blocks are already functional building blocks as part of the compiler decision to what to implement. So the compiler chooses the arithmetic operation and then the equal, because we have equal. And for this specific example, we see that actually the implementation is having an MCX with 2 controls and two NOTs. So we have a NOT before and NOT after, and this is in order to have the control on the proper state. So it can be seen as a control on the state 0 as well. But now if we are connecting this to the previous or the first homework that you had, is we have the oracle function, we have the phase kickback, but when we drill down and we view it on the underlying implementation, we see a multi-control node. And here we can actually understand that when the compiler comes to implement this oracle phase kickback, it has many options to implement the underlying circuit. Because in the first homework, what you did is that you compiled for a multi-control node with 5 qubits, you compiled 3 different implementations. And then when it was a multi-control node with 20 controls, you've seen that there are many more implementations, and they differ in terms of the circuit depth and the circuit width. So now we can see, and then we discussed only the multi-control node. So it was one very specific building block, and now we went one level up to a quantum primitive or to algorithmic building block. So the algorithmic building block phase kickback uses let's say, one component called multi-control node. And now when you understand that the multi-control node has many possible implementations, you also understand that this phase kickback, the oracle phase kickback that now we've designed in a functional way, so we didn't thought about the actual underlying implementation, it has many different implementations. So it's not even logical to discuss only one implementation, because as you viewed, we can synthesize for different constraints or for different optimization parameter, and then we'll have different implementations for the same algorithm, for the phase kickback. So here we can see some the information, and as you can view this new version of Classic, it has some changes in the interface. Now we can also execute it, and we can also execute it with the state vector simulator. So until this point, we used only the classical simulator or the regular simulator of Classic. Now we use also the state vector simulator, and we can run. And now with the state vector simulator, we receive these 4 possible values. So we have here an encoding of the phase. We see 3 values with one with the same phase and 1 value with a different phase. Unfortunately, now there is no interpretation of the bit string. So if we want to understand the bit string in terms of the value, the integer values, we can also execute it with the regular simulator and then compare the bit strings and their values. But even without seeing, so actually we know that 0, 0, 0 means the value of 0 for x. So this is what we wanted. And we can see that it has a different phase. So here there is the encoding. And here the phase is 0 for this and a phase of pi of -1 for the others. Now you can think about it that you have a global phase of -1 and then everything flips. So if you add a global phase, it doesn't change anything in quantum computation. So just have in mind that you're adding a global phase of pi or of -1 to all the components here, and then the 3 components of 1, 2, and 3 will have a pi phase, so it's -1, and the phase of 0 will be 0. So here you can see the legend, the encoding of the phases, and you can see the amplitude. So the phase kickback doesn't change at all the amplitude, right? So as we view in the graphical way we presented things, so the amplitudes do not change. So we can see here that the amplitude of all the components is the same. So we started with an equal superposition, we remained in an equal superposition. The only thing that changed is the phase of the thing that we were interested in. And this is super cool that we can actually view it. And this is also a nice tool in learning. And when we're trying to understand, we can use the state vector simulator for small scale examples, because when we actually want to understand the phase, and it's not something that is useful for actually gaining advantage from quantum algorithm, but for learning and for understanding, it's a useful tool, as we see here. So now we can understand and simulate the phase. And in the exercises that you do now, you also should use it in order to understand the phase and the phase difference. And on another note, you can do some other algorithms that create some interesting rainbows, let's call it like this, here. So you can, this is also a nice exercise that you can do. So think about what kind of algorithm you can make in order to have some interesting rainbow that goes across all the palette of colors of the phase. So this is another tool that you should use, and this is how you use this state vector simulator. Now, this is the exercise that I want you to do now. So I will leave this screen open, and then we will go for a 5 to 10 minutes break. And during this time, you can start with the exercise to implement. And this exercise, as always, you can continue at home. This is an optional exercise, but it's highly recommended to do it. And in the canvas, you can see or either now or later, you can see the optional exercise and the homework that you have. So what you need to do now is, from the phase kickback implementation that we viewed how to go to the model tab, and then from this to the tutorials. So from the IDE, create a quantum algorithm that flips the phases of the values x equals half and x equals 0.75 for an input state of 3 qubit that is in a superposition of the values of all the values between 0 and 1. So for this, you should create an equal superposition, so we can see a value of 0 and 0.125 and 0.25 and so on and so forth. And what you should use is the allocate num function. So maybe you used it before, maybe not, but there is the allocate. So this is a general initialize, how you initialize either a qubit or a quantum register. You can use it also for quantum numbers, but then it won't have a specific encoding. Here we see that we will have a specific encoding for our states. So it's not just a superposition of 0 and 1 and 2 and 3 until 7. We have an actual underlying decimal interpretation or other numbers interpretation for arithmetic interpretation for the state that we have. And for this, if we have non-standard, so non-integers, non-regular integers, numbers as the arithmetic interpretation, we should use the allocate num or initialize a quantum number. For this, you can use the reference manual for allocate num, and you should execute the algorithm with the state vector simulator to verify your algorithm, as we did now. Now, last thing before the break. So from the documentation, you can search here, allocate num, and then when you press on the definition, you can see the syntax that you have. So it's the number of qubits and if it's signed or not. So if you want to have also minus values or not. So for this example, you should just write false. And then fraction digits. So how many fraction digits? It means, and for this case, you should use 3 qubits and 3 fraction digits, because you have, as we've seen here, so we use 3 fraction digits or 3 digits after the decimal point, and this is the interpretation that we use for the quantum number. So you should use the allocate num. You can search in the reference manual in the search bar, or in the documentation in the search bar, the allocate num, and to read a bit more about it. So now we will take 5 to 10 minutes, let's say, until 8 minutes break. So we still have 1 more minute for the break, but I see already 2 questions in the Discord. So I see a question. So how do I make target x equals 0.5? So the same way we did it for x equals 0, this is how we do it for 0.5. But when we want to have for 2 values, we want to flip for 0.5 and 0.75, but actually what we need to write over there is x equals 0.5, or, and actually to type the word or, x equals 0.75, and then we'll have we'll flip if we encounter either the 0.5 or the 0.75. So this is one question. And the second question is, where do I put the input quite of 3? I'm not sure I understood the question, but maybe it's how you initialize with 3 qubits, and then this is in the allocate function. So the allocate or allocate num. Yeah, so for the qubits is allocate, so you can initialize with the allocate function, and then you do with 3 qubits. And as you can see here, you should use the allocate num, and then in the allocate num, you have all the variables and the arguments of the function that you need to incorporate, and one of them are the number of qubits you want to have the state with. So yeah, exactly. And the target should be as YW7593 just wrote. Okay, so let's move on to the second quantum primitive of today's session. And this is linear combination of unitaries. Now, this is the last quantum primitive that we will cover for the module. And next week, we'll cover a more general quantum framework. But this is quite an advanced algorithm. So this is used in many applications, many state-of-the-art applications, but the quantum primitive itself is quite advanced and quite is more involved. So we won't cover the full details of it. We just give the high-level scheme, high-level overview, and then there is a tutorial that I'll show you where you can find it in the classic documentation, that you can actually go step by step and understand it more carefully. So we'll cover the motivation, we'll explain the high-level working of the algorithm, we'll go through the implementation high level, and then I'll give you some use cases examples. And this is really interesting because we can see already really advanced use cases being used by this linear combination of unitaries primitive. So the question at hand, or what the linear combination of unitaries, or in short LCU, want to address, is how to apply a non-unitary operator in quantum computation. So this is a bit of a surprise, right? So we know in quantum computing, we have only unitary operations, but suddenly we can ask the question, or we have encounter a question like this. So how to apply a non-unitary? So this is sort of a game changer, but let's see how we can apply it, and how we can actually understand it in terms of the things that we know in the model of quantum computation, where on the high level, quantum computation or quantum computer only allows us to evolve or apply some unitary operators. So how we cover the bridge. So this is the algorithm addresses this. So the input of the algorithm is a quantum state psi, And a non-unitary operator, A, so we can think of it's just a matrix, so it's a non-unitary matrix that is decomposed to a sum of unitaries. So for the algorithm, in order to be applied, we need this non-unitary matrix A to be decomposed and hopefully in a good way, in a nice way, into some linear combination of unitaries. And this is the reason why the name is a linear combination of unitaries. So alpha I are real positive coefficients. So these are just real numbers. And UI are unitary matrices. So we can think maybe about the two unitary matrices that we know, let's say the identity and the Z Pauli. So these are two unitaries of 1 qubit unitaries. Unitaries applied on 1 qubit, and we can add them together. Let's say 0.5 with the identity plus 0.5 of the Z operator. And then we will receive a non-unitary operator, a non-unitary matrix. So this is how we can think. We decompose the matrix, the operator that we have, into the non-unitary operator into a linear combination of unitaries with some coefficient. This is the input. And the output is the application of A on psi up to normalization factor. So the normalization factor of the alpha, of the alphas. And in the tutorial, you can read the exact the calculation of the normalization factor. But in fact, we apply this non-unitary on the state side. Now, there is small cheats over here, or things that I swear under the rug, because there is some entanglement to other register that must be taken into account. And in a moment, I will briefly go over it. But on the high level, we actually apply some non-unitary operator on a state side, which is apparently really a useful tool. It's also related to block encoding of the matrix A. So if you see this term, so it's also related. And let's dive into more details through a concrete example. So again, we'll understand it from a concrete example, and then in the tutorial, you can read more carefully the explanation. So here, what we have is some general non-unitary matrix A. So it might be also unitary, but it might not be unitary. So we have these coefficients. It's a linear combination of 4 different unitaries with 4 different coefficients. And the state we have initially is the 0 state. So we want to apply A, this non-unitary, or in general non-unitary, on the state psi. So I'm showing you along the way the actual implementation, how it applies. So first we have this state psi. We initialize it to the 0 state. And then the first step is we prepare another register according to the alpha coefficients. So ignore for a second the unitaries, the unitary decomposition. View only the coefficients alphas. So we want to prepare a state that starts from 0. So this is another register. It's not the psi. So we have here on top the psi. On bottom, we have another auxiliary register, or the prepare register, that we prepare in a superposition of the states according to the alpha coefficients. So again, here should be a normalization factor, but on the high level, we prepare the coefficient of the 0 state alpha 0 according to the linear combination of unitaries coefficients, and the coefficient of the 1 state to be alpha 1, and so on and so forth. This should be normalized, but let's ignore the normalization for a second, just in order to understand it in a more intuitive way. And then the heart of the algorithm is called sometimes select. So what we are doing is we applying a control version of the unitaries, control on the values of the prepare register. So what does it mean? Let's go step by step. And here just the order is different, but what we can see here is controlled or conditioned on the value of the prepare alpha or the prepare register being 0. Control on this, apply the U0 unitary, and control the control on the value of 1. So the value of 1 should be here. So it's 0 for this qubit and 1 for this qubit. So this is the general value of 1. Apply the U1 unitary. Controlled on the value of 2. So we can see here, apply the U2 unitary. And for control on the value of 3, apply the U3 unitary. Now, we should have in mind that we first prepare the prepare register, prepare alpha. So in classic, you can do it by prepare state and then input or just type the alphas that you have. So if you have a 2-qubit state for alpha, so 4 values of alpha, you should have a prepare state with a list of 4 values. So alpha 0, alpha 1, alpha 2, and alpha 3. And then the second part will be to conditioned or controlled by the values of the quantum state, the coefficients applied to specific unitary. This is the second phase. Now, the last part will be to prepare alpha inverse. And this is a key part in the algorithm. And now we can also, something that should pop into your eyes or in your mind is that we have this method of prepare and prepare inverse. So for this, we will use the within apply of classic. So this is a common construct or a common framework or way of doing things in quantum algorithms. So we have this, we're preparing something, we prepare some state, we apply some other operations, some functions, some unitary evolution, and then we do the inverse operation. Now, continuing the explanation, after we do the prepare alpha inverse, so it's just the inverse of the unitary we applied here. If we measure the component here to be in the 0 state, then what we want to achieve, the output of applying the non-unitary on the value of the initial psi. So for this example, the initial psi was 0. So we actually applying what we want. So what we need to do here is to sort of post-process only for the values of 0, or we can do other ways. For example, we can measure, or we can train, if it's a quantum machine learning algorithm, with the swap test. We want to be close, and we want to actually be with the 0 value. But only if we are applying these 3 steps. So we prepare alpha according to the decomposition that we have of the A non-unitary. We prepare alpha, prepare state. We applying control unitaries. The controls are according to the state corresponding to the alpha coefficients. We prepare alpha inverse, and then only if we measure in this register, the prepare register, the value 0, so only for 0, we know that the action that was applied on the initial psi state is the action of A, the non-unitary A, up to a normalization factor. Now, how it can be, and now we can understand in a more general way how it can be that we apply a non-unitary operation on quantum computers. So what we have here, it's called the block encoding, or we encode A in a more general unitary. So this is why we need these also auxiliary or prepare registers, so additional qubits, and then we apply the non-unitary operator, but it's only a sub matrix of the unitary matrix that is applied over the entire quantum computation. So this is also why we need to limit, or only when we measure 0. So if we measure 0, we can think that we view only submatrix of the entire unitary matrix representation of the algorithm. And then within this submatrix, so it's a special or specific area within the general unitary matrix representation, we apply the non-unitary matrix of A. So this is why we need to measure in the auxiliary register or in the prepare register, we need to measure the state of 0, and then we actually implement what we want to achieve. And this is really cool and really super useful quantum primitive, and it's in fact sort of quantum algorithm by itself that is used in many applications, but because it's so common, so we can call it a primitive, but it's sort of an advanced primitive. Now, you have in the classic documentation, the tutorial, and this will be your guide or how you should continue for doing the homework. And you can dive into more details from the tutorial, but from the documentation, so docs classic IO, you have the explore section, and then in the tutorials you have linear combination of unitaries, and then you can view the implementation, and you can view it also in GitHub. At the moment, it's not in the IDE, so it's not in the platform itself. It will be there hopefully by the next week or in 2 weeks, and then you can also directly view it over there. But from this tutorial, you should have the ability to understand all the code, and then also to implement it both in Python and in the native Qmod language. So let's discuss some use cases where it is used. So this is a general framework of quantum algorithms, and there is a paper called Grand Unification of Quantum Algorithms, which is an extension for this paper. So quantum singular value transformation and beyond. So if you see quantum singular value transformation or transform or QSVT, know that this is a general framework that many quantum algorithms, if not all quantum algorithms, but many of quantum algorithms, including the algorithms that we know, so search algorithms and matrix inversion, all of them can be explained or can be achieved by this framework of quantum singular value transformation. So this paper, we can see that in part of the paper, so addition, subtraction, linear combination of blocking code and matrices. And in the paper, what they wrote is we use a simple but powerful method for implementing linear combination of unitary operators on a quantum computer. So this is a key building block in this state-of-the-art or advanced technique and papers, so quantum singular value transformation and blocking coding or linear combination of unitaries. So this is what we covered here. It's a key thing, so it's a simple but powerful method for implementing the things required for this algorithm. So this is really nice because now you have one part of this advanced framework that you can understand, and this is a key part. So now when you are going to read some advanced or state-of-the-art quantum algorithm papers, research paper, you have one more tool that you understand how these were implemented. And again, this linear combination of unitaries is a common building block in many state-of-the-art implementations. Now, another implementation is Hamiltonian simulation by qubitization. And this actual paper, you might be use this method of qubitization in the final project. So this is also especially useful for the Wominium project and the Wominium program, in addition to the general understanding that is super useful. But for the project phase, you might be using the qubitization. And also here, they say that this approach to Hamiltonian simulation, so qubitization is another approach to do Hamiltonian simulation. And I think two of the papers, the key papers that you should implement in the final project are dealing with Hamiltonian simulation. So there is qubitization. It's a method for implementing one of the key papers that you need. And linear combination of unitaries is a key part of this method. Now, here's the abstract. So in the abstract of this paper, they explain or they state that they use this linear combination of unitaries because it's a key building block, a key quantum primitive within the qubitization method. So here we can see two advanced state-of-the-art algorithms or frameworks of doing some meaningful quantum algorithms, and linear combination of unitaries is a key building block, a key quantum primitive in both of them. So I really recommend understanding it first on small examples on the low level. Be comfortable with some use cases, some extreme cases of the linear combination of unitaries on small scale. Be more familiar and get the confidence in your understanding the algorithm, and then you can also take one step further and read some of these example papers, so qubitization of quantum singular value transform, and try to spot where they use and how they use this linear combination of unitaries as part of their algorithm. So I will show briefly how you can view the tutorial on the platform, but the homework assignment, and this is for submission. So what you need to do, it can be stated quite easily. So you should apply a non-unitary matrix, and this specific non-unitary matrix, on a 1-qubit quantum state, which has a probability of 0.3 to be measured in the 0 state. So this is nice because it can be stated quite simply, but to actually do it might be more complicated. But again, I think without knowing that there is some algorithm called linear combination of unitaries, how it's working, and that it applies some non-unitary matrix, it would be very, very hard even to start thinking how you can implement this matrix on a 1-qubit quantum state. It's non-unitary. It could be confusing, but now that you know that there is another tool set, another quantum primitive that enables you to actually implement some non-unitary matrices, or non-unitary operators on quantum states that you want. So it opens a new maybe dimension or a new family of matrices and operators that you can implement with quantum algorithms, and this is a super useful technique. So before we go into the project description, let's view in the documentation. So if I'm going to the documentation, you have in the Explore page, you have tutorials, and then you can view here linear combination of unitaries. So this guide tutorial, you can see the matrix and decomposition into the alpha i's, and then the wording that is used here is prepare and select. So prepare is the prepare alpha, the first step of preparing, and then select is the act of the control unitary. So if I'm going back to the circuit, so prepare alpha in the tutorial and commonly in the literature is called prepare. So we prepare the state of the register alpha according to the coefficients alpha I, and then the second step is select. So we select or control on the specific value, we apply some unitary. So this is called select, and the last phase will be prepare inverse, because we inverse the initial preparation. So as we can see here, we do prepare, and then we do select, and the last step is prepare minus. And this is what we mean by doing an encoding of A. So we encode A in a larger unitary. So this is a mathematical way of describing it. And then what we actually do is we apply the non-unitary matrix A on the quantum state that we want. But we encode A with the linear combination of unitaries in a more general unitary, because at the end we can only evolve unitary matrices or unitary operations on a quantum computer. So this is another scheme that you can view. So it's a prepare and then select. So select, you should have in mind these controls. So condition on the specific value, we apply a control unitary according to the values of UI. And here you can read more about the within apply. There is a specific example here that we want to demonstrate. So we want to apply some non-unitary matrix. So it's the identity plus the quantum Fourier transform plus the inverse of quantum Fourier transform, and you should go over the example. And then you can see that this is how we do the select part. So the linear combination of unitaries, the LCU controllers, this is the select part, and we can view the underlying circuit. So control condition on the value of 0. So if the controller, the value of the Qnum controller is 0, so then apply the identity matrix. So this is what should be done here. And then conditioned or controlled if the Qnum, the quantum register, the value is 1, so apply the QFT, and so for 2, apply the inverse of QFT. And here you can see that the control probabilities. So the probabilities are applied or are defined, and then there is a prepare state of the controller. So in place prepare state. So there's prepare state and in place prepare state. So you can read in the tutorial, but the fact that in place prepare state is used is in order to have the inverse prepare state. So these are some nuances, because always there are some nuances in implementation that you should read carefully, and only when you actually implement it, you encounter these nuances. But on the high level, you prepare the state according to the probabilities, and we apply it as part of the within apply operation, as we can see here. So we do an in place prepare state according to our probabilities. And then what the action that we want to do is the LCU controllers. So this is the first building block. And again, this is quite a short code, a simple code that prepare the desired function. And here you can view all the code together. So here 2 functions, the main function and the LCU controllers, and then the actual linear combination of unitaries is applied. So again, I'm going back to the homework assignment that you will have. So the previous exercises are highly recommended, but optional exercises. And this is the homework assignment for today's session. So you should apply the non-unitary matrix 1, 0, 0, 0 on a 1-qubit quantum state. which has a probability of 0.3 to be measured in the 0 state. And in the canvas, there will be the specific deliverables that you will have to do and you have to submit. You can do it either on Python or in the native Qmod. At the moment, you have the tutorial available only in the documentation, only with the Python version, but you can add at the end one line of code and maybe it's written over there. So there is a function called write Qmod, and then it transforms the code, the model from Python to Qmod. So then you can also view it in Qmod. So this is also a nice way to interpolate and go from and transition from the Python code to the native Qmod. This is the homework assignment you have in Canvas, and I will be also available for questions for this assignment via Discord and in the next session. This, in fact, ends the session on quantum primitives. So we covered 4 primitives. We covered the swap test, the Hadamard test, the phase kickback, and linear combination of unitaries. And these are 4 key quantum primitives, key quantum building blocks. A swap test and Hadamard test, I think they're a bit more simple and intuitive, and also very useful tools. And today we covered the phase kickback and the linear combination of unitaries. These are a bit more evolved and advanced, and also use a linear combination of unitaries, especially is used in many advanced and state-of-the-art quantum algorithms. So now we'll do some project Q&A. So I will again cover on the high level the classic model within the Minion project, and I hope now things will be more concrete and you will understand them more. And then there will be some time for questions, for Q&A regarding the project phase itself. So the classic idea of Minion summer program, we have the project, so the phase 1 of the Minion summer program. So there will be 3 key papers. So it's classically verifiable quantum advantage from a computational Bell state. The second is exponential quantum speedup in simulating coupled classical harmonic oscillator. And the third one is evidence for the utility of quantum computing before fault tolerance. You will implement one of these key papers, and in the next slide I will cover how you should approach implementing them. But on the high level, you will decompose it into the very toy problem first. So you just take the main algorithm that is used in the paper, and then you just implement a toy problem of the algorithm. So for example, here there is Hamiltonian simulation in the paper. So the key thing that they are using is the key algorithm they are using is Hamiltonian simulation. So first you will just implement a small example of Hamiltonian simulation, maybe even not related to the paper itself. This is only in order to understand or to verify your understanding that you know what's the key thing, the key algorithm in the paper and how you can implement it. Next, you will try to come up with a small implementation of the problem at hand. So for example, in this paper, there are some aspects of how you encode the data. And again, this relates to the previous question of what does it mean encoding, but here you need to encode some data about the classical oscillators into the quantum computer. And this is not done with quantum machine learning frameworks. So there are no parameters that should be tuned over there, but there's some classical parameters, or there is a way to encode the data about the classical oscillators in the quantum algorithm, and then it being evolved using the Hamiltonian simulation, and then there should be a readout, so a smart way to measure. So first, you are only try to implement the heart of the algorithm. So in this case, Hamiltonian simulation. Then you'll try to also add the encoding part. So to encode in a smart way, but a small problem, a small toy problem of the actual problem at hand. And then you'll try to take the last step forward and to implement the general quantum algorithm in the paper. And then one step further, it will be to optimize it to different scenarios. So even when you approach implementing a state-of-the-art paper, there are several layers or several levels you can come up for the implementation. And this will be the way you should approach it in the phase. Now, the training part that we built for this project phase. So we covered the classic 101. Today we finished the second session of quantum primitives. And next week we'll cover quantum walk. So this is a general framework for quantum computation. and quantum algorithms. The second part of the training will be some talks by key researchers and researchers of some of the key papers. And then we'll cover in a more detailed way, but more concrete algorithms and applications using Classic. So first, there will be, we'll cover discrete log implementation. So this is, we can think about a variation of the Shor's algorithm or a cousin of the Shor algorithm from the same family of algorithms. But again, when we come up to actual implementation of algorithms, there are many nuances that we need to deal, and it's far from being simple, or it's way more complicated in a way, just reading a paper or an understanding in a theoretical level, and then to come up to implement it, you should have more understanding. You should first understand the theoretical parts very well, but you should also come up with smart ways to implement and to overcome all the nuances and obstacles along the way. So there will be one short session about discrete log implementation, another session about Hamiltonian simulation with Classic, and the third session about advanced quantum arithmetic. So all these, or most of the advanced quantum arithmetic, will be super useful in when you address the first paper. So when you address classically verifiable quantum advantage from a computational Bell test, there are some advanced arithmetics involved over there. So the fourth point over here will be super useful for this. Hamiltonian simulation would be, I think, useful for the second key papers, and the discrete log implementation. I think there are some building blocks over there that will be useful for all the three, but I'm not sure it could be tied directly to one of them. But it's viewing other implementations. You can have some ideas or some ways you want to implement things that you have seen in other algorithms. So actually, all of them will be super useful for all the papers that you will approach. So I'm putting here from the definition of the project, the phase one, the deliverables, and I'm open to questions now.
Okay, perfect. Yeah, thanks a lot, Aiden. I think the participants are very excited for the project. And now we can have live Q&A with Aiden regarding the project. So I would suggest all the questions to go on Discord, and then I can take them one by one. Just a reminder, the soft deadline to register your teams and select your project is in 2 days. So team up, see who all are interested in participating in the Classic Challenge, and register your teams on Canvas as soon as possible. If you want to invite new people to the challenge, maybe you know some friends from universities or at your institutions, invite them too, right? Just have them register on the Romanian program, and then you can all together team up and participate on the Classic Challenge. What is in it for you? There are a lot of exciting prizes. Number one, there are Romanian grants for all the winning teams. And in addition, the best of the best of the best will be selected for QSL fellowships and a phase 2 project with Classic. So that is the best thing that can happen, right? Do a project in 1 month and then get a chance to work alongside some of the best researchers there are at Classic. So yeah.
And also one possibility that would be, so from some very good or excellent projects, maybe the implementation themselves would be interesting enough to publish some papers and peer-reviewed papers or conference papers out of them. So implementing a state-of-the-art algorithm is something that is interesting for the community, the research community in general, and also for, and maybe nowadays especially also for the industry, but also for the research community. So for interesting projects, there it might be extended to writing up a paper regarding the implementation.
Right, yeah, absolutely. And we all know the value of getting some useful publications out there. So if someone is interested in working on the research end of algorithms, maybe improving it, even using certain quantum error correction tools alongside it, I know it's a far reach within a 1 month time frame, but yeah, if you work really hard, you can achieve a lot of amazing stuff. So who knows, at the end of 1 month and at the end of the 3-month fellowship with Classic, you might be in a very, very good position in the industry to publish some really good papers along with it. Okay, yeah, we are receiving some really amazing comments. Rachna says, as a try, she would love to be Eden's doctoral student. So yeah, now it's up to you.
Yeah. I'm not a professor, so I cannot be a proper supervisor, but I will be happy to supervise for the project. And I think there are some really interesting stuff and opportunities nowadays in the quantum ecosystem, and especially in quantum algorithms. And actually, all the materials that we covered in this module, so these quantum primitives, it's in the majority of the quantum algorithms courses that are available in most universities, top universities, and all universities. These kind of building blocks and algorithms are not really part of the curriculum. So it's really things that are quite new in the ecosystem and are getting into being the standard, but it's a new material out there, and I think it's really great for the opportunity here to present them as part of the summer program, and then you have the option to play around, to understand, and to actually come up with the implementation of these building blocks.
Right. We have another question on Discord, and this is related to one of the papers you mentioned about evidence of utility of quantum computing before fault tolerance. So the question is that if we are applying error mitigation tools to a certain algorithm, we also need to test it on real hardware. So is there a possibility can Classic provide certain credits for using real quantum hardware, or maybe we can use certain noise simulators to run their simulations?
Yeah, so that's a good question. There are several ways. So first, as you said, there are noise simulators that can be used either from Classic or to integrate on top of Classic. So at the end, you design your algorithm on a functional level with Classic, you compile it, you synthesize to a specific circuit implementation, and you can have, as we've seen, many circuits implementation. Once you receive the circuit implementation, you can export it as a cousin code. And once you have a cousin code, so it's the underlying implementation, you can also integrate with other packages. So for Mythic, for example, it's another package that is the input for things used in the package for functions in the package are some quantum circuits. So you can input the cousin circuit that you exported from Classic and integrate it with the Mythic package to apply some error mitigation techniques and use the simulator available from the Mythic package. So you can do some use some noisy simulators within Classic. You can also integrate with other Python packages as well. And a third way is, yeah, for a good project, we will have the option also to give some credits to run on real hardware. I cannot promise now for all the projects, but it will be case dependent. But in addition, there are some providers. So I think in maybe AWS Bracket and also in Azure in Microsoft, there are free credits for students around the world. So you just sign up, and when you sign up, you receive, I think, usually it's like $500 free credits that you can use. So you receive the credits from the providers, and then you can use them within the Classic platform. So you'll receive over there the credits with some credentials, and then when you come to execute from the Classic platform, you will just need to insert the credentials, and then your user will be connected to the provider, and you can use the credits.
Right. Yeah. And Classic has very generously offered a pretty decent amount of hardware credits to the participants. So if your solution is really good and you're confident about it, just write us a mail explaining why do you want access to real quantum hardware devices, and then we can coordinate with Classic and issuing you certain hardware credits. And we also have some hardware credits available through Womanium's a partnership with other quantum providers. So Qmod is there, Strangeworks is there, and a few other quantum providers are also out there. In case you need certain very specific hardware credits, just let us know and we'll try our best to make that happen. Okay, one other question, and this is not exactly regarding the project, but a more general question. According to you, Eden, which industry does the exponential quantum speed up in simulating coupled classical oscillators mostly affect?
That's a great question. Yeah, the short answer is I don't know, and that's an interesting question. I'm not sure anyone knows, but I'm trying to think out loud here. So, firstly, for classical physics and maybe not proper industrial use cases, but for classical physics and for the research community of classical physics, I think it can be there are many. So, oscillators, so harmonic oscillators in quantum and in classical, it's a key framework or key building block that we describe almost everything in terms of harmonic oscillators. So simulating these classically can be useful for many physical problems. I can think maybe, so I'm not sure here, but I'm thinking out loud, maybe in things related to lasers. So there are some parts we describe quantum mechanically with photonics and quantum theory of light, but some parts we describe classically, and over there we have some we use the models of classical harmonic oscillators. So maybe there are some complicated problems in the industry regarding lasers, and lasers are used all across the industry. So in manufacturing and in your iPhones, you have lasers, and in sensing and depth. So lasers are all around. And so it might be that there are some interesting open questions, or even not open, things that now we do some heuristic, or we do some numeric simulation that are not accurate enough. And then with this, once quantum computers will be at the point that they can actually give some concrete advantage also for industry. So maybe in 5, 10, 20 years, nobody knows, but maybe when we reach to that point, so there will be some application, I don't know, interesting question within things related to lasers and sensing that can be used with this algorithm. Wait, Vardan, I think you're on mute.
Oh, sorry. Yeah, I'm saying thanks a lot, Aiden, for that. And Rolando Soma from Google Quantum AI would also be coming to our program. So this question would also be, suitable for his stuff. So you should directly ask him about his paper he has authored.
Definitely, that's a great.
Another question is, can you explain the application on the first paper you have listed over here, classical verifiable quantum advantage from a computational bell test? What exactly are the applications from this paper?
Yeah, so this is also a good question. So I think the key point over there is to have some protocol, and we can think about it maybe in terms of quantum communication, but we can also have it on a quantum computer. And it might be, or a follow-up works of this kind of algorithm might be the first theoretical, the proven first theoretical advantage of quantum computers. So all the theory of quantum advantage and quantum supremacy, and now there's the world of quantum utility, is quite a mixture, but we haven't yet proven experimentally that we can, we haven't demonstrated on real hardware that there is quantum advantage per se, that there are the tasks that quantum computer are proved to be more useful, exponentially more useful than classical computers. And this specific paper can be one of, or maybe is one of the candidates that can be in the quite shorter term implemented on a quantum computer and actually experimentally verify that we have this notion of quantum advantage. So this can be really interesting. And there are still some open questions in the follow-up research over there applied on this, but this can be a huge thing. So the first experimental evidence of quantum advantage is something that all the community we seek for and we want to see. And this paper or this line of research is one option for actually verifying this.
Perfect. Another question is, which algorithms would you suggest are similar to Deutsch-Jozsa's algorithm for finding expected values?
Which algorithm are similar to Deutsch-Jozsa in terms of finding expectation values? I'm not sure I fully understood the question. So they are finding expectation values in general, and the Hadamard test that we covered last week is one option to finding it. The Deutsch-Jozsa, for example, it uses another primitive that we've covered today. So the phase kickback is used over there. I'm not entirely sure what the question addresses.
Yeah, if you could just clarify your question in Discord, that would be great. And yeah, I think we are almost nearing the end of the time as well. So if there are any more questions, just keep the conversation going on Discord, and we can also shift the conversation to the specific project channels we have on Discord. Eden is also there in Discord, so you can directly ping him and ask him any particular questions you want about the project. And yeah, rest assured, we are really looking forward to a lot of teams participating on the Classic project, eventually some of the best participants winning it and coming on and doing another 3 months of the project as a fellowship with Classic and Romania. So yeah, very excited and looking forward to all of your solutions.